All right, objective one, first introduction to sequences. There are just a few, pieces of terminology that I need you to know before we actually move into identifying types of sequences and that type of thing. The objectives we're going to cover, eventually we're going to be able to determine the explicit formula for a given sequence, but initially we're going to determine whether the sequence is either arithmetic or geometric. And after we're able to do that, then we'll be able to determine the explicit formula and then generate terms in a sequence given the explicit formula and identify patterns of a sequence and generate additional terms. And then we might be able to get to apply sequences to real-life scenarios and problems if we have time. To begin, though, a sequence is any ordered list of numbers. In this sequence, so for example, 2, 5, 8, 11, 14, and 17 is considered a sequence of numbers. This ... just means that it goes on forever. So there's terms you'll hear later in this module, infinite and finite. This is infinite because it goes on forever. That's what those dots mean. Each number is considered in a sequence to be a term. So please be following along and writing this down as I'm writing as well. So it's a term within the sequence. So these terms are referred to in a subscripted form as, I'm going to write a sub n. Each subscript refers to the, position or placement, I'll put position, of a number in the sequence. So a sub 2, that is a sub 2 in the sequence above. So a sub 2, let me erase this. A sub 2 then is considered the second term. So in this case, the second term in my listing is 5. So a sub 2 is 5. Now, take a minute and consider what would a sub 7 be and then a sub 10. Now, how many terms are in here? There's 1, 2, 3, 4, 5, 6. So what is, let's say, a sub 6? In this case, a sub 6, the sixth term is 17. So the sixth term is 17. In order to find a sub 7 and a sub 10, you're going to have to consider the pattern. These numbers are going up by a specific number each time. You're going to have to consider what that number is, and then hopefully in class we can go over a sub 7 and a sub 10, and hopefully you'll be able to know what they are. I'm not going to tell you what they are. So moving on, when sequences have a definitive pattern in a given sequence, we are able to figure out what we call the sequence's explicit formula. In order to find the explicit formula, I'm going to pause on that thought. We are going to eventually find the explicit formula, but before we do that, I have to discuss the two types of sequences. So to finish out this page, the two types of sequences, the first one is called the arithmetic, and the other one is called the geometric. These are considered to be the two types. They each have their own specific explicit formula, and we're going to work through how to find the explicit formula for both after we practice determining the difference between and identifying an arithmetic versus a geometric sequence. So, let's begin with arithmetic sequences. Arithmetic sequences go from one term to the next by adding the same value. Arithmetic are pretty easy to work with. Now, adding the same value, you need to come up with the, hopefully just to visualize it initially, especially if they're lower numbers, you have to find what's called the common difference. These numbers in this sequence are being added by the same common difference each time to get to the next number. 2 plus what equals 5? 5 plus what equals 8? 8 plus what equals 11? Hopefully it jumps out at you. The common difference is 3 for this sequence. The next example, 7, 3, negative 1, and negative 5, is a little bit difficult, a little bit more difficult, I would say, because you're technically still adding, but in this case, the numbers are going down. So you have to consider what is the difference. 7 plus what number gives me 3? 3 plus what number gives me negative 1? Negative 1 plus what number gives me negative 5? In this case, the common difference is negative 4. So some people consider, since it's negative 4, that it's just 7 minus 4 is 3, 3 minus 4 is negative 1, and so on and so forth. But for the sake of just arithmetic sequences, we're going to consider everything to be adding to the next number, even though it's a negative. You can add a negative and get lower in the sequence. So the number added each time is called the common difference. And it's represented, this is important to consider, by the letter D. Because we're going to use D in the explicit formula in a little bit later. Now, in order to find the common difference, sometimes it doesn't just jump out at you like up here, 2, 5, 8, 11, 14. It's pretty easy to see that it is 3. If you ever are in a situation of a sequence that you can't necessarily immediately think of the difference itself, then the actual way to do this is you pick one term in the sequence and subtract the term before it. Meaning, in this sequence, 3, 11, 19, 27, 35, if that's not easily seen, you take one term, it has to be the one at least before the first one, so 11, and you subtract the one before it, 3. 11 minus 3 is 8. So if I was going to do this again, just to check my work, I would take the next term, 19, and subtract the one before it. 19 minus 11 is indeed 8. Just to triple check, 27 and 19, 27 minus 19 is 8. And the difference between 35 and 27 is also 8. So that is just, if you're dealing with bigger numbers and you can't quite see the difference or mentally figure it out initially, then that's the actual way. You take at least the second term and subtract it by the one before it. So the common difference here is 8. So that is arithmetic sequences. Arithmetic sequences. The biggest thing with arithmetic is the difference is the same, the common difference is the same, but you're adding a number each time. There is one key difference, adding and now moving into geometric sequences. Geometric sequences go from one term to the next by multiplying. Multiplying by the same value. So it's the same value each time. One is just adding for arithmetic and multiplying for geometric. So in this case, let's look at this sequence. 1, 5, 25, 125, and 625. What number do you multiply to 1 to get 5? That's the question I would ask myself if I was trying to figure this out. What number do you multiply to 5 to get 25? In this case, it jumps out pretty quick that it is indeed 5. Now the next example, down here, 48, 24, 12, 6, hopefully it jumps out at you that the numbers are getting smaller. So you have to multiply by a number that's less than 1. 48 and 24, the relationship is, I visualize, and then 24 and 12, and 12 and 6. It's going down, it's half of each other each time. So I'm multiplying by a factor of 1/2. Again, some people might consider that dividing by 2. 48 divided by 2 is 24. But also 48 times 1/2 is 24. So we're going to keep it in the multiplication terms. Now again, sometimes it won't be able to jump out at you that easily. So in order to find the common ratio, you pick one term, not the first one, and divide it by the term before it. So let's start with 4. 4 divided by the term before it, 1 is indeed 4. Moving to the next one, 16 divided by 4 is 4. 64 divided by 16 is 4. If you need to use your calculator, go ahead and do it. And just to check our work, 256 divided by 64 is indeed 4. So this common ratio is 4. I'm so sorry, I didn't note another key difference. Geometric sequences, I think I talked about this earlier. Yep, is ratio. If you notice, it's common ratio for geometric and common difference for arithmetic. D and R specify are a huge jumping off point of what we're working with, either arithmetic or geometric. So, things to remember for the end of this video. If you add the same value to get from one term to the next, you have an arithmetic sequence. Arithmetic sequences have a common difference. If you multiply by the same value to get from one term to the next, you have a geometric sequence. Geometric sequences have a common ratio. Ratio because you're multiplying, difference because you're adding for arithmetic. Sequences without a common ratio or common difference are neither. Those do exist, but they're neither geometric or arithmetic.